Hello class, this is Ms. Riggins with today's video on sections 7.1, Integration by Substitution. As you're watching the video, please remember to write down important information, statements, equations, formulas, graphs, or examples, and feel free to pause, rewind, or replay the video as often as you need so you can get a clearer understanding about what's occurring in the video. And at the conclusion of watching the video, write a brief summary about what occurred in the video in your notes and submit that summary via the online WISC online the day before class, as well as a top question. Now today's video is going to be a little bit longer because it's going to be chock full of examples which you guys have requested, and in this unit we're going to need to use a lot of different examples because to describe what's going on, which is an integration strategy called the substitution method. So if you recall, in the past, if we wanted to be able to integrate a problem, we would have to use some elementary integrals that we already know, as well as the last unit we talked about constructing a function based off of the second fundamental theorem. But today we're going to do something strictly algebraic, which I know you will enjoy. Okay. Let's take a look at this problem right here. Off the bat, some of you will say, oh, there's no way I can integrate this. I can integrate maybe the first part, the 3x squared, or I can maybe integrate cosine of x, but not cosine of x cubed. But one of the things that you may notice is that the input of cosine is x cubed, and the derivative of x cubed is 3x squared, which is what this is being multiplied by. And this may have you remember, this looks very much like a chain rule, which looks something like that. The derivative of the composition of two functions is going to be equal to the derivative of the outside function with respect to the inside function times the derivative of the inside function with respect to x. So in this case, it looks like cosine is the derivative of the outside function with respect to x, and 3x squared is the derivative of the inside function x cubed with respect to x. So this starts with the chain rule, or the substitution method is all about. So in order to use the substitution method, you must first identify what function is going to be the w, and it's going to represent the inside function of a composition of functions for your antiderivative. So if w is the inside function, then the dw, this is the inside function, then dw is going to be equal to the derivative with respect to x times dx. And that's basically saying, well, this right here is the same as this. So multiply both sides by x, and you get dw is equal to w prime of x dx. So let's actually do that for that particular problem. Let's identify what our w function is, and then identify what dw is. So as you can see here, we're going to let w be equal to x cubed. That's the inside function of some composition function. And then cosine of x cubed now then would represent the derivative of the outside function with respect to the inside function. And since the w is x cubed, then dw is going to be equal to 3x squared times dx. Okay? And once you have that, we're going to replace the integral and take out all the x's and replace it with w. So as you can see here, this now becomes cosine of w times dw. And this is exactly what we want, because we do recognize this as an elementary integral, and we know that the integral of cosine of w is sine of w plus some c value. So we're almost finished, because now we have an answer, an antiderivative, but our antiderivative is in terms of w, and we need it to be terms of x, so we replace what w is equal to, and we get our final answer as sine of x cubed plus c. Okay? So let's try that on another problem. So let's go back to this page and let's try that on this problem. In this case, we have the integral situation here. And if you notice, x to the fourth is part of the square root, but then the derivative of x to the fourth involves x cubed. So let's let w be equal to x to the fourth. So that means dw is going to be equal to the derivative of w with respect to x times dx. And that ends up being 4x cubed times dx. So now I can but I need exactly what the x cubed dx, because I don't have a 4. So if I divide both sides by 4, then I have here, which is I finally have x dx, which is this part and this part. And then this part is just essentially the square root of w. Okay, so now I can solve this problem by replacing everything in here with what I have. So x cubed dx is the same thing as 1/4 dw, as we saw here. And this is the same thing as square root of w. Bring the 1/4 out, and then this looks very familiar, a popular integral, elementary integral we just find by doing the power rule, a version of the power rule. And we get our final answer to look something like this, but we have to replace the w with the x, and we get our actual final answer to be this, and we have to add the c. Okay? All right, so now another question may be, how is it that this substitution method works? Well, let's go back to our chain rule. More specifically, if this is our chain rule, if we were to integrate both sides of the chain rule, so let's integrate here and integrate here, then we end up with something that looks like this. Actually, I have to switch it around. This part right here goes right here, and this part right here goes right here, because the integral of the derivative ends up being the antiderivative, okay? And if I let w be equal to g of w, in other words, my inside function, if you recall, and then dw dx will represent g prime of x, I end up with replacing this entirely by saying this part is this part, and this part is this part. Okay? And that, in doing some simplification, we have certain things cross out, we have this cross out, and we end up with this, which is essentially what we're doing. We're letting our integral be something in terms of a function with respect to w times dw, and we will get our answer like this. And that's, as you saw, is what we did there as well. Okay? So, oops, didn't want you to see that. Hold on. So some more examples. So here we have this situation, and using the substitution method, what should we let w be equal to? And again, you're looking ahead, and this looks very familiar. Take a look at your elementary integrals that you know how to integrate and try and get this in terms of it. So I'm going to let w be equal to 1 plus t, e to the t. So therefore, dw dt is going to be equal to essentially e to the t. And then dw is equal to e to the t dt. Why is that important? Well, since this is what w is equal to, oops, didn't want that one. This is what w is equal to. And since this is what dw is equal to, then I can entirely replace this integral in terms of something involving w, 1 over w dw. Okay, I don't know why I have the extra one. Okay, and hey, this looks very familiar, like a very popular elementary integral, which is the natural log of the absolute value of w plus c. And then because we have what w is equal to, then our final answer, we have to always return it back to the variable that we were talking about, is this answer, which is natural log of 1 plus e to the t dt. Okay, let's try another problem. Integral of tangent theta d theta, which is not an elementary integral. And I know some of you are saying, well, I don't see the derivative of tangent, which is 1 minus secant squared. You're right, you don't. But let's do this, which is represent tangent in terms of sine theta and cosine theta. And then some of you may be able to say how you could use the substitution method. Hint, hint, look right above what we just did. So in this case, I'm going to let w be equal to cosine of theta. So dw d theta will be equal to negative sine theta. So dw will be equal to negative sine theta d theta. So what we have right here is we have our w, and then we have our dw, which is it's supposed to be, it's negative sine theta d theta, but we don't have a negative, so what we're going to do is we're going to put a negative out here. So it's negative dw, okay, which is what this is, because sine theta is d theta is equal to negative dw, okay? And then we can still apply the same popular elementary integral to negative natural log of w plus c, and we get our final answer by replacing what w is in terms of theta, okay? Hope you're getting the hang of it, because we have some more examples. But the strategy in all for this is to guess an expression for w and hope to find a multiple of dw with what is left in the integral, is what we did here in this case. Now, just in the same process for evaluating the indefinite integral, we can also evaluate the definite integral using that same process. First, treat it as if it's an indefinite integral, and then find your answer, and then evaluate it at the integral. So we're going to look at two strategies. As we can see here, let w be equal to x squared. So dw dx is going to be equal to 2x. So dw is going to be equal to 2x dx. So here we have our x squared, and here we have our dw, 2x dx. But as you can see here, we have x dx, so that must mean we're going to have to put out a 2 in the outside of the integral just to make this work. 1/2 outside the integral, and that's what we do, and we end up with this answer, okay? But since we have limits of integration, then we can evaluate our answer in terms of x at those integration points, limits of integration points, and we get this as our answer. Another strategy is a little bit different. I mean, you'll get you the same answer, which is we've already changed this and kept the answer in terms of w, and then the idea is, well, if w is equal to x squared, then if x equals 2, then x squared is 4, and if x equals 1, x squared is 0. So therefore, we really have this answer in terms of w, and we really have this limits of integration for w, and therefore you can skip having to ever go back to the x part and just leave it at this. Potato, potato, it's the same thing that we're doing, okay? So, in general, how do I use the substitution method to find indefinite integrals? You can do two ways. You can compute the indefinite integral expressing the antiderivative in terms of the original variable, what we did, which was x, and then evaluate the result at the original limits of integration, which were 2 and 0. Or we can convert the original limits to new limits, which we did, with w is equal to from 0 to 4. And do not convert the antiderivative back to the original variable because we're actually computing the definite integral and we don't need to. So it's up to you which one you want to do, okay? Okay, last one, and this is a really complex one, and so it really is a trick of being able to identify what do you think it should be as your w. That's the trick. What should your w be so that you can use an elementary integral, because you were able to represent the original problem in terms of w in an elementary integral type way. And some of you may be saying, oh, well, I'm going to let w be equal to the square root of x. Well, if you let w be equal to the square root of x, dw, which is going to be 1/2 over the square root of x, is nowhere in this integral. So I can't really let w be equal to square root of x, but I can let w be equal to 1 plus the square root of x. And therefore, w minus 1 will be equal to the square root of x, but w minus 1 squared will be equal to x. And then, if I take the derivative of both of these sides, I get 2 times w minus 1 dw is equal to dx. Tricky, huh? It is. But I like that because now I can actually replace the original integral in terms of things involving w. So 1 plus the square root of 1 plus x. Well, this is my w, so this is my w, and then my dx, oops, I didn't mean to copy that dx, but my dx is equal to this, okay? So if that's the case, then now this problem becomes this. As you can see, w, square root of w, and then 2 times w minus 1 dw. Tricky, isn't this? I know it is, isn't it? And then we can integrate that by simplifying into terms that we can algebraically integrate, and then using our popular or elementary integrals come up with an answer, and then replace that answer in terms of x, and voila, you have your answer. So I know this video is long, but like I said, it was because I'm doing a lot of examples, and you're going to have to do a lot of examples to be able to figure this out, because I know some of you are like, well, how would you know how to do that? Practice makes perfect, okay? All right, thanks. Bye-bye.